Okay, so to solve systems of differential equations using the chain rule, we will rely, guess what, on the chain rule, okay? And actually, this is a great method to solve non-linear systems. You know, the systems we got to solve in the previous few sections, that is using the eigenvalues and eigenvectors and using the Laplace transform. Those were linear systems of equations. We never had the unknown function or their derivatives raised to another power or part of exponentials or trig functions or the like. This time, have a look at this system. Notice how the dependent variables in this case, which are x and y, the unknown functions, are non-linear. But the question here is, how does the chain rule help here? Okay, well, so suppose from calculus 1, guys, this is check. When you take the derivative of some function dy dx, okay, or f prime, what do? You do dy du times du dx, unless you have more functions in the composition. But in this case, I'm talking about a composition function composed of two functions only. Of course, that can be bigger if you have more. Okay, guys, I'm going to change the game a little bit here. So I'm going to do this dt instead of du. And do you guys agree that dy dt, I'm going to multiply by the reciprocal or dx dt, which is another way to say the chain rule. And that's the trick, guys, to solve the PDE. That's it, right? You're like, wait, what the hell is going on here? You'll see. Okay, so example 1, solve dx dt equals to x squared plus xy, and dy dt equals to y squared xy. Okay, so number 1, let's use the chain rule to a chain rule setup. Okay, so well, essentially this is going to be equal to g of x y divided by f of x y. Okay, and which is what we're going to do here. So do the setup: dy dt divided by dx dt. Okay, that equals y squared plus xy divided by x squared plus xy. All right. How about we cancel the dt's right here, okay, to make this simpler. So this will be dy dx equals, I'm going to do some algebra here. I'm going to factor y in the numerator. That's y plus x. And in the denominator, I'm going to factor x plus y. And these two terms are going to go away because they're common factors. What does that result into? Dy dx equals y over x. What is this, guys? Week 1. This is a separable equation, isn't it? How about we solve it and see what we get? So that'll be dy over y equals dx over x. Integrate both sides. That's ln of y equals ln of x plus some constant that I'm going to call c. And then I'm going to use a different constant later because we're dealing with a system in this case. Okay? And well, exponentiating both sides. So e to the ln of y, what is that equal to? Isn't that equal to y equals to um, e to the ln of x, that is simply x. But what is e to the c? Isn't that just another constant? Okay, let me multiply that over here in front of the x. Actually, let me make some room right here. I should have done it over here. Much better. Okay? Okay, so this is our number 2. Okay. Okay, guys, let me go back to dx dt. Dx dt equal to x squared plus xy. Actually, guys, this is y equals to cx, which I'm going to substitute into the y into the first equation. All right, the y in the first equation. That'll be uh, dx dt equals to x squared plus xy, well, not xy, well, let me xy, yeah, dx dt equals to x squared plus x times cx, all right? And well, this is x squared plus cx squared, which in this case, factoring dx dt equals to dx dt, that equals to, what is that? Let me factor x squared, that'll be c plus 1 times x squared. And I know we could absorb the 1 with the c, but actually I'm going to leave it like this, okay? I'm going to leave it like this in this case. Okay, so guess what? This is another separable equation, isn't it? This is another separable equation, dx over x squared equals to c plus 1 dt. Integrate both sides. That'll be, okay, essentially the integral of x to the negative 2 dx, which is, what is that? That is, let me continue. Okay, let me continue all the way up here. Up here, that'll be negative 1 over x, right? Equal to the integral of a constant times t, that is the constant c plus 1 t plus a second constant d. All right? Because that's out of a different solution. Okay? All right, guys. What about all of this? I would like to solve for x. So number one, I'm going to multiply both sides by negative 1 over x equals to negative c plus 1 t plus d. Do not distribute the sign. Just leave it like this. And then just flip everything over. Everything right here is understood to be divided by 1, isn't it? Just go flip. X equals to negative 1 over c plus 1 t plus d. So that's the x solution. We still need to go back and find the y solution. How do we find the y solution? You might wonder, for the y solution, don't we have this equation for y times cx? So y equals to cx when y equals to c times all this madness here, negative 1 over c plus 1 t plus d. Let me just reduce. Oh, that's actually final answer for x equals negative c over c1, I mean c plus 1 t plus d. All right? Essentially the same solution, right? And that is the solution to the system. It's interesting, right? How two totally unrelated concepts like the chain rule. How does that okay, just think about how does a chain rule have to do, what does chain have to do with systems of equation? But nothing, right? Well, that's a very clever trick to solve uh pretty cool systems. One more and we're done. Okay. All right, how about that system? dx dt equals to e to the x divided by 2y. And dy dt equals to e to the x. And guys, don't even try to find the eigenvalues and eigenvectors, nor don't even try the Laplace transform on this one. It's not going to work. Chain rule is going to be your best friend here. Okay? Chain rule. All right. So let's get started by setting that chain rule. dy dt equals, I mean, divided by dx dt. And that equals, okay, so the y, which is e to the x, divided by the fraction e to the x over 2y. All right? Okay, guys, here, dividing by a fraction, it's the same as multiplication e to the x by the reciprocal, that is 2y divided by e to the x. And the e to the x's, guess what? They go away, all right? Also, we can cancel out the dt's right here, and write our initial separable equation. dy dx equals to 2y. Okay? Separate, solve. The rest of the story, we saw something like this before. All right? Let's do it, of course. dy over y equals 2dx. Integrate both sides. ln on the one hand. Actually, you know what? To make some room, let me do it. Let me do this over here, right? That is, yes, ln of y equals to 2x plus some c, all right? Okay, so what do we do from here? Let's exponentiate both sides, all right? Exponentiate both sides and wait a minute. And cancel e with ln. That's y equals e to the 2x. What about e to the c? Isn't that another c again? Right? And well, we have the solution for y, which go to the first equation, y equals to c e to the 2x, and substitute in there, right? That is dx dt equals to e to the x over 2c e to the 2x, okay? Let's do a little bit of algebra of exponentials. It's a little bit algebra exponentials. That is, okay, e to the x and e to the 2x in the denominator. That's going to leave us with dx dt equals to 1 over 2c e to the x, which is another separable equation in x and t. Okay, let's solve such equation. E to the x equals to 1 over 2c dt, and integrate both sides. I mean, the integral of e to the x, guys, isn't that just e to the x? E to the x equals to 1 over 2c t, okay, because the dummy variable here is t. And what do we need to add here? Another constant, right? In this case, d, because this is out of a second equation we were solving, all right? Well, you might want to solve for x right here. What do we do to get the x by itself? Natural log, okay? Take the natural log on both sides. ln, ln, and that equals x equals to ln of, 1 over 2c t plus d, okay? And that is the solution to for the x function, all right? What else do we need? Oh, we need the y solution. Y solution. How do we get the y solution? Okay, guys, to get the y solution, go back to the highlighted function here. You already have it solved for y. However, check this out. You may not, okay, one thing you might be thinking here is to substitute this logarithmic term into the x here. You wouldn't be able to cancel it with ln right away because you have the two. You would have to do the basketball rule of ln's to be able to cancel them, right? However, is there another way? Is there a plan B? Okay, remember when before we took the ln's right here, we have e to the x equals to something. Well, substitute the something there with a little twist right here. Check this out. Y equals c to the... Okay, do you guys agree that e to the 2x is the same as saying e to the x raised to the second power? Let me get rid of the ln's for a second here. So let me use a different highlighter. E to the x equals this madness here, right? Just go back and substitute there. That's it. How about that? So y equals c 1 over 2c t plus d quantity squared. All right. And that's it, right?